This is AP Physics, and today we're pondering RC circuits. So, shown I have two different circuits, one with a resistor and one with a capacitor. Let's consider why we put these things in a circuit. If we have a resistor in a circuit, well, without the resistor there, we would only have wires, and with only wires, that would be a short circuit. There would be no resistance. We would have charges, many charges flow, heat up the wire, and burn out the wire. So we place a resistor there to oppose those charges from flowing, to reduce the amount of charges flowing, or to reduce the amount of current, so that when we close the switch, we get charges flowing, and then that energy, the voltage from the battery, the energy per charge, is being dissipated into heat, into light, converted into whatever that resistance is. Now, when we place a capacitor in the circuit, its role is very different. The capacitor is there to be able to stop charges from flowing, because in between the plates of the capacitor you have an insulator, so the charges cannot flow across there. So when you close the switch, charges will flow out from the battery, but then when they get to the plates of the capacitor, they will stop there, and you will end up storing the charge on the plates of the capacitor, and in storing that charge, you store electric potential energy associated with those charges. Now, when you have just a capacitor in your circuit, when you first throw the switch, there are no charges that are on the plates of the capacitor. So then charges will rush out, in large quantities to the plates of that capacitor, which means you would start out with a very high current. So initially that current spike can heat up wires, damage things in the circuit. So then when we put the combination of the two into a circuit, kind of on the most basic sense, that resistor is opposing that sudden spike in current, and making the charging of that capacitor more gradual. Considering an RC circuit then, so the circuit here I have drawn, you've got a battery, you've got a switch that can go to A and B, a capacitor and a resistor. If we want to charge up that capacitor, then we would throw the switch to location A. So in our diagram here, if I move that over to A, that is in a position whereby the center branch is kind of out of the mix. So we'll just cross that off. It's not connected to anything. However, your capacitor and your resistor are in a closed loop, a complete circuit with the battery. This is a position whereby you will charge the capacitor, but again, with the presence of the resistor there, you will not charge it instantly, but it will occur over time. Now, it's important that you realize that it occurs over time, because what that means is that your current will not be constant, because when the capacitor first starts to charge, the current will be higher because there's no charge buildup, and as the charge builds up, then the current level will drop down because you get a backup of charges. That also means the charge on the capacitor will not be constant, obviously, because it's building up. Now, if these two things are not constant, then what we need to do, kind of our goal for this, is to be able to derive equations down for how that charge builds up and how that current changes after that switch is thrown. So at a time of 0, that's when we close the switch to A. And so we need a Q of t and an I of t equation. thinking in terms of what we've been doing with Kirchhoff's laws. Loop rule. If we apply a loop rule to this circuit, going around, again, from any arbitrary point, I'll choose the upper left corner, and I'll go around the circuit in a clockwise direction. Our base equation, since we have capacitor and a resistor in here, our base equation for capacitor is C equals Q over V. Our base equation for resistor, Ohm's law, V is equal to IR. So let's fill in the quantities and then talk about the signs. The voltage across the capacitor, if I solve C equals Q over V down for V, I'm going to get a Q over C. Now, I'm writing that as a lowercase q because capital Q would represent the maximum charge, so we want to indicate that it's the charge at any given point in the process, so lowercase q. When I get to the resistor, your voltage is I times R, and then continuing around when I get to the battery, we have an EMF. Now, loop rule, when we combine these, we're going to get a 0. Now, let's think in terms of the signs of each of these. Okay, your battery, we can think of in terms of a positive, the EMF. In that sense, what it is doing, it is supplying the voltage, or is supplying the energy per charge. In that context, then, your resistor is dissipating, so I'm going to put a negative on there. And your capacitor is storing charge, so I'm going to put a negative on that one also. Now, that's our base loop rule equation. We have to recognize one thing, though. This current, being that it's not constant, if I leave that current in there as an I, that makes us think that it is a value. Since it's not a value and it's changing, we're going to have to substitute dq dt. Okay, so if we rewrite the equation, negative q over c minus, I'm just going to flip the order, r dq dt plus the EMF is equal to 0. Now, I'm going to add probably more emphasis to this than we should, but it needs emphasis here. This equation is a differential equation. Oftentimes when you're solving down on an AP problem, they will tell you, set up a differential equation. Once you put that dq dt in, you have a differential equation. Okay? Differential equations are not hard to set up, but they can take a little bit to be able to solve down. So we have the differential equation there, and our goal is to solve for Q, more specifically to solve for a Q of T equation. So then with this differential equation, to be able to do that, I'm going to do some algebra. First, I'm going to look at isolating the dq dt onto one side. So then if I go to negative r dq dt on one side, and then move everything else over to the other side, so then I'll have a positive q over c and minus the EMF. Now, I'm going to get a common denominator over there on my left side, or on my right side. So to do that, I'm going to have q minus c EMF over c, and then on the other side, negative r dq dt. Now, I'm going to throw the r onto the other side and also the negative. So dq dt, q minus c EMF over negative rc. I'm going to get rid of that pesky negative by just moving it up top. So then I'll have C EMF minus Q over RC. Now, we've got the Q on one side and the dq on the other side. So a little bit of algebra here. I'm going to flip-flop, keep the dq on this side, and move the C EMF minus Q over to the other side. Okay, and then I have 1 over RC left on that side, and I'll move the dt over here. So basically I've cross-multiplied or partially cross-multiplied to be able to do that. Now, all the Q's are on one side, and everything else I could possibly move to the other side is over on the other side. So we are ready to integrate here. Okay. On my right side, the integration is pretty easy because R and C are constants. So on the right side, when I integrate with respect to time from 0 to t, all we're going to get basically is a t. Let me move that down a little bit. We're going to get a t over RC. Okay. On the left side, a little bit more complicated. Okay, so I'm going to do a U substitution and let U be equal to that denominator, C EMF minus Q. And so then du dq would just be a -1. So then dq would be equal to negative du. When I put that in there, then what I'm going to have is the integral. In place of a dq, we'll go negative du. In place of C EMF minus Q is just u. So I have the integral of negative u du. Rewriting that, integral of u to the negative first power du. That negative sign I'm going to throw onto the other side to get it out of the way. So it equals negative t over RC. Now when we integrate that, we're going to get the natural log of u, and that's equal to negative t over RC. Now putting back in what we previously had, natural log of C EMF minus Q. Now the endpoints of integration, thinking way back up to when we started the integral, we are integrating with respect to Q. When we first closed the switch, there was no charge on the capacitor, so our endpoints of integration, 0. And then we are approaching, as we build up charge, some other charge Q. And so then I'm going to get natural log, when I plug in endpoints, of C EMF minus Q minus the natural log of just C EMF is equal to negative t over RC. So then writing that difference of natural logs as a ratio, this is going to be natural log of C EMF minus Q over C EMF is equal to negative t over RC. Making a little more space here. I'm going to come up over on the side over here. To get rid of that natural log, I have to raise both sides to E, or the base E, and so I'm going to get C EMF minus Q over C EMF is equal to base E to the negative t over RC. Now, from there, it's algebra. What we're solving this down for is that Q. So in doing the algebra to be able to solve down, I've got C EMF minus Q, multiplying the denominator up to the other side. C EMF equals base E to the negative t over RC. I'm going to subtract the C EMF to the other side, so negative Q is equal to negative C EMF plus C EMF base E to the negative T over RC. Throwing the negative on the other side, I'm going to do a couple algebra statements here. So Q is equal to, with a negative on the other side, that I'll flip my two signs on the other side. So I'm going to go make that positive, that'll become positive, this will become negative, and then I'm going to flip around the order of those two. Actually, I'm going to factor out a CEMF. CEMF, and that'll be 1 minus E to the negative T over RC. So that is your Q of T equation. Now, that was half of our original goal. The rest of our original goal was to find an I equation. Well, I is equal to dq dt. So when we take the derivative of that, I'm going to have the C EMF. That's just a constant. It's just going to kind of hang out. Derivative of 1 is 0. Derivative of your negative E to the negative T over RC is negative E to the negative T over RC. Applying the chain rule, though, we have to take the derivative of what's in the exponent of base E, and the derivative of negative T over RC with respect to time is going to be a negative 1 over RC. Now, algebra to simplify, our two negatives are going to drop out. So then putting all the constants out front, I have C EMF over RC E to the negative T over RC. My C's will divide out, and then I have an EMF over R. By Ohm's law, that's a V over R, which would be an I. So I'm going to call that I sub 0, and then E to the negative T over RC. And that is our I of T equation. Now, a couple things on a couple of our symbols here. So, our two equations. When you are charging your capacitor in an RC circuit, charge C EMF 1 minus base E to the negative T over RC. CEMF from our relationship C equals Q over V. So then Q would be C times V. If that's a CEMF, then that's going to be your maximum charge. So I'm going to restate that as a capital Q, where capital Q represents maximum charge. Your I of T equation, I naught E to the negative T over RC. Now, let's analyze that a little bit. Okay, if we think about Q max, what it is and when it occurs, I max, what it is and when it occurs. In your RC circuit, when you first throw that switch, there is no charge buildup. Okay, so when you start at time equals 0, Q is going to be at a minimum. It's going to be at 0. Now, if you think about your Q of T equation, mathematically, if you plug in a time of 0, you get E to the 0 power, which is 1, And then in your parentheses, you get 1 minus 1, which is 0. So that reinforces 0 charge. Okay. Now, in your I of t equation, though, when you plug in a time of 0, e to the 0 is 1. And so your maximum current, I naught, which would be your EMF over R from Ohm's law, that's going to occur at a time of 0. Flipping back over to Q max, we know at the start Q is equal to 0. Okay, well, if you plug an infinite amount of time into your Q of t equation, that would basically be Q times 1 minus e to the negative infinity. Well, that would be 1 over e to the infinity, and 1 over e to the infinity is going to go to 0. Okay, and so then you get 1 minus 0, or Q. So your maximum charge is going to be Q, and it's going to occur after an infinite or a long period of time. Okay. Conversely, on a long period of time, if you think about your current, okay, if you plug into your current equation a t value of infinity, you get e to the negative infinity, so 1 over e to the infinity, which approaches to 0. 0 times I naught is 0. So then your current goes to 0 after an infinite time, or realistically a longer period of time. So you start with high current, you end with low current, you start with low charge because it's not charged up, and after a long period of time you approach fully charged. So it approaches it as an asymptote. So if we look at graphs, charge versus time, current versus time, your charge starts at 0 and it's going to rise over time and approach an asymptote. It's going to approach that maximum charge, and that maximum charge value would be a CEMF. Your current value, on the other hand, starts high and then exponentially decays, and that maximum current value, I naught, which would be EMF over R. Very important that you go beyond just trying to memorize what does what at what point in time, but you understand the process of how we arrived at the equation, okay? And you understand what's going on when. Now, let's think about the term that has showed up in our equations here. Ponder for a second. Now, you got a term that has shown up within the exponent, base e to the negative t over RC. Well, that RC we call a time constant using our Greek letter ta. Okay, yes, it's a symbol for torque, but we use it for time constant also. That is equal to R times C. Okay, we name that as a time constant because really that is what is controlling how this charges up or discharges. Okay, if you have larger R and larger C values, okay, you're going to extend it out. If you have shorter values, you're going to increase the rate at which that charging process occurs. So let's think in terms of the time constant, which is really a time value. So even though we're multiplying R times C, in the equation we would think of that time value in seconds. So let's say our time value is equal to 1 time constant, which would be a value of R times C but we would express that in seconds, okay? In our Q of t equation, Q times 1 minus e to the negative t over one time constant, I'll write RC, okay? Now, at one time constant, then our time is RC, so I'm going to erase the time there, and I'm going to put in an RC there. So then basically that would be Q 1 minus e to the negative first power, and e to the negative first power is a 0.368. Well, that's going to give me 1 minus 0.368, or about a 0.632. So then 0.632 Q, so that at a time equal to one time constant, our capacitor is going to reach 63.2% of maximum charge. If we apply this same logic to our current equation, I naught e to the negative t over RC would basically be our value of 36 or 0.368. So then at a time equal to one time constant, we get 0.368 I naught, or our current will have dropped down to 36.8% of what the maximum current was when we first threw the switch. Okay, so using the time constant is a convenient way, since you never fully charge the capacitor and you never fully drop down to zero current. It is an easy way to think in terms of percentages, how charged is a capacitor after one time constant or two time constants, etc. Now, let's talk about applications of RC circuits. Basically, what you have added in this whole process by putting them in combination with each other is the factor of time. So when you need things to occur over time, or you need to charge up the capacitor and it takes a period of time, an RC circuit is useful. RC circuits are used in things such as camera flashes. If you've used a disposable camera, or a camera probably besides the one on your phone, because it wouldn't be obvious on your phone, whenever you're using the flash, you have to wait for a few moments for that flash to be able to charge. What you have in there is an RC circuit. It is taking time to be able to build up charge on that capacitor, and then when the flash is ready, you use it, completing the circuit on a different path to be able to use that energy very, very quickly to get that flash of the light bulb. By the same idea, RC circuits are used in pacemakers, because a pacemaker is something that's going to need to deliver a charge in a regular time. So you use an RC circuit to build up charge when it is at the appropriate voltage to deliver that shock across the heart. Okay, that voltage level trips a switch, which then completes a circuit and has the discharge. So RC circuits are used for a lot of things where you need something to occur at a regular period of time, perhaps a little closer to home, on your car, the turn signal. When you turn the turn signal on, it flashes at a very regular rate. Well, that's an RC circuit charging up and then discharging and causing a flash, and then charging up and then discharging and causing a flash in a very regular fashion. If you have ever had the blinker light bulb burn out on your car, what happens is the signal light then flashes very, very rapidly, much more rapidly than it normally would. And what's happening there is, in the RC circuit, the resistance value has changed because now you have a burnout bulb instead of a good bulb. With a different resistance value, that changes the time constant, and with a different time constant, you reach the voltage, the discharge voltage, more rapidly, and so you discharge more rapidly and you get a rapid flash. Anything that has to occur at a regular period of time, okay, also on your car, intermittent, windshield wipers, okay, those intermittent windshield wipers, you turn the dial. After a certain period of time, they wipe your windshields. You turn the dial differently. What you were doing is dialing up a variable resistor, and that variable resistor is changing the time constant of the RC circuit. And so it's changing how often you reach that voltage that trips the windshield wipers to go on. So a lot of timing circuits use an RC circuit within them to be able to get something to occur at a very regular time period. Now, what we summarize in this video is basically what an RC circuit is and how to be able to charge up a capacitor in an RC circuit. In the next video, we'll talk about